Okay, excuse me. Time is 12:30, so let's get started here. So assignment number 6 is due Friday at noon. Today we'll start talking about the graphics section. Are there any questions before we get going here? Okay. So, as we've discussed before, R is organized into packages. These packages contain functions and sometimes even data sets inside them. There are 3 main packages in R that can be used for graphics. The first one is the graphics package. This is often referred to as traditional graphics because this is what essentially was available first. And then there's also the lattice and the ggplot2 packages. Of those two, ggplot2 now is a lot more popular. To be honest, my favorite package to do graphics or plots is the graphics package. Not everyone necessarily shares my opinion. This ggplot2 package, which came out about 6 or so years ago, has gained a lot of followers. For example, the New York Times, if you see a lot of their cool graphics that they have in their newspaper, they often use ggplot2 for those. I personally think some of the defaults in ggplot2 are not very good. Also, it often takes, in order to get a plot completely done, meaning let's say publication quality, it often takes just as much code in ggplot2 as it does in the traditional graphics package. So, because obviously we have time limitations, I'm going to start with the traditional graphics package. And if we have time at the end of the semester, I'll talk about ggplot2. I think all people who are doing stuff in R should at least learn the graphics package. Okay. So far, we've actually been using the graphics package. That plot function lives in the graphics package. And what we're going to begin with here today is ways that you can add content to plots that have already been created. And this is actually fairly easy to do in R in comparison to other software. And we've actually even done this already. So if you remember when we did a Scatterplot for the GPA data, we added the estimated regression model to the plot. We added confidence interval bands to the plot. That was one example of how you can add information to a plot. So let's add some more information to basically that same plot. And I think oftentimes when one is describing how to do graphics in any software package, oftentimes it's helpful to first take a look at the final product before you actually take a look at the code. So this is the actual graph that I want to construct. And we've already constructed parts of it already. The thing I want to add is the prediction intervals, and it's not going to be too difficult. But the new thing here is how to add a legend to a plot. Okay. So just to review, I'm going to work with the GPA data here. So I'm going to read in the GPA data using read.table. And I'm just reading in the plain ASCII text file that's space delimited. Then I'm going to use the LM function to estimate the regression model, put the results into mod.fit. Then for the plot itself, for the scatter plot, I specify what my x-axis variable is, what my y-axis variable is. Notice how I have some nice grid lines that are going to be put on the plot first. To do the estimated regression model, and we talked about this at the end of class last time, I'm going to use the curve function, where my expression in terms of what I want to evaluate or what kind of mathematical function I want to evaluate at 101 equally spaced x points, I'm going to use the predict function. Notice here for new data, I have a data frame, and I'm putting in X there for high school GPA. Next, I can do then the confidence intervals. And again, we did this before, where I basically use the same code, but I take advantage of the fact that predict also does the confidence intervals, and I extract out the second and the third columns of what is actually produced by the predict function to get the lower and upper confidence intervals. Okay, now to do the prediction intervals, same exact code, except for I specify in the predict function itself, I want my interval not to be confidence, but prediction, or predict the prediction intervals. So now I'm finding an interval for y, not the expected value of y. And then lastly, the legend. Please note that there's a small, very small typo there. Now, in many software packages, legends are almost kind of automatically drawn for you. And in fact, that's what essentially happens with ggplot2. What I have found, though, through my experience, is that I often need a lot finer control of exactly what's going to be in that legend. And so one aspect that I like about the graphics package is I have a function called legend that allows me basically to construct the legend by hand, where you could say, I want to specify the exact location for it. I'm going to specify the exact contents of that legend. So to do this, let me actually come on over here to 10. So to do this in my legend, I'm going to specify x coordinates and y coordinates to put the legend. So at x equal 2, meaning high school GPA of 2, and then a college GPA of 1.25, that's where I want my legend to be. Now the labels for what's going to be in the legend, I specify using the legend argument. Okay? And all I'm doing here is I'm combining together 3 labels. Okay? Then also I'm going to say, well, I don't want a box drawn around the legend. Sometimes I do, sometimes I don't. The default is to have a box. I don't think I need one in this case, so BTY for box type equal quote n end quote gives me no box. The color. Well, I need to specify what each of the lines in the legend represent by the color and also by the line type. So first for color then, I'm going to specify, and this is where the typo was, that corresponding to my first label, which is estimated response, meaning the regression line itself, that's going to have a color of red. The 95% confidence interval bands had a color of blue, and so on. Then lastly, for line type, well, what we saw in the plots was the estimated regression model, as was plotted, was a solid. Confidence interval was a dash, and the prediction intervals was dot dash. So once I highlight the code, run it, take a look at my plot, and there I have a nicely placed legend that nicely describes everything. Are there any questions? Yes?
So for the sequence plot different curves, you just like, if you want to plot those circles on the top of the graph, do you know what I mean?
No, I don't. I'm sorry.
I mean,
Can you restate that?
The line is, looks like the line covers part of the circle. So I want the circle on the
You want the circle
top layer of the...
I mean, I guess I don't really see that as much of a problem. I guess I always think of plotting the data first before you plot any lines on the plot, because how are the lines coming about? It's coming about through the data itself.
So,
but if you did want the circles on top, there is a way that you could do that. And basically you need to plot the circles last.
okay.
How? Here's how. I'm going to do exactly the same code as before, except for I'm going to put an option here for the first plot. I think this is the option. If it's not, then I'll have to look it up. Nope. Okay. Look up real fast. There we go. Notice how I plotted it without anything actually appearing. How did I do that? I added this option here, type equal n for no, I don't want stuff. There's many other types that you could look at. You take a look at the help for plot.default to see them. Okay. And then I do all my curves. So there's all my curves. And then lastly, oops. Since I already have a plot, I don't need to use plot again. And instead what I can do is use a function R called points that I was going to talk about later. That just plots points. So let's see if this works. And there you go. The circles are drawn on top, and maybe, if we make them a little bit thicker, you would see that better.
So how you write the code sequence beside them? How you lay it out?
The sequence of the functions corresponds to how stuff is added, and you could say in terms of layers. Any other questions?
So, for the assignment, we have to draw this plot. So, do we have to add legends there?
It would be nice. Well, let me see what I did for the answer key. I think I know what the answer is, but I just want to verify. In the answer key, I did not put a legend. The reason being is because, at least when I construct these assignments, I think of, okay, this assignment's over sections, the introduction section and the regression section. You already have enough information as of the last class to do the plot. And so that's where I kind of had the breaking point. Sure, you can add a legend. You know how to now. But if you haven't already, well, then don't worry about it. But any plot that has multiple lines or multiple plotting characters in it should always have a legend to describe what it is. Any other questions? Okay. So let's see. Well, there's other ways to get a legend on a plot. Let me get a new plot out here. Rather than specifying x and y coordinates, there is you can specify instead something using a function called Locator. Locator 1 means that you're going to click on the plot in one location, and that's where the legend is going to be dropped in. So it's a little bit maybe, depending upon the circumstances, might be more of interest. So same code as before, except for now, look at what happens to my mouse. It's a plus sign now, because it's asking me basically to add the legend to the plot. And wherever I click, let's click up here just to see what happens. Wherever I click, that's where the legend's dropped in. Okay? Now there are times where, if we look at the legend, there are times here with this legend that the amount that the line type is sampled, meaning, and I don't mean sampling in the statistical sense, but basically, that legend there, those line types there are, to illustrate what the line types are for a particular plot. And sometimes, especially depending upon the line type itself, it may not be clear that, that's a dotted line type versus a dash line type, or that's dot dash, or that's a dot dash, or something like that. And so I have found that at times it's often nice to have a larger line given in that legend. And the way to do that is to use a seg.len argument for length in the legend function. There's an illustration of that in my program. Please see that. Also, when you are actually plotting when each plotting character has a, let me restate this. Let's say if you have multiple different kinds of plotting characters in your plot, and rather than maybe illustrating the different line types, maybe you want to illustrate the different plotting characters instead. So instead of an LTY argument in the legend function, you might need a PCH argument in the legend function, which stands for plotting character. Same PCH that we used previously with in the plot function. Also, there may be times where you want to actually put the legend outside of the actual main plotting area. So maybe instead I wanted to put this legend for some reason, let's say up here or down there. Maybe you needed the space. There's a way to do that. It's not necessarily as easy as maybe one would like, but I give an illustration of how to do that in my program. Please take a look at it. And it involves using the par function with the XPD argument. Remember, the par function allows you to control various graphics options. XPD basically allows you to draw stuff outside of the main plotting area where you have the points, where you have the lines. And by saying XPD equal true, I believe it is, or it's false, what's in my program, you're able to draw some stuff outside of it. You can put the legend outside. Okay. Now, sometimes, too, you might want to label points or put any kind of text anywhere inside the main plotting area. The way to do that is to use the text function. This allows you to add text to the plot. So, for example, in this plot right here, you can see that I've actually added observation numbers for some reason. Maybe you wanted to know that. I've added observation numbers to this plot. So let's take a look at how this is done. So simply say text, put in your x coordinates and your y coordinates where you want to put the actual text in the plot. So in this case, I want to put text in 20 different places because I have 20 observations. So notice how I have vectors for x, I have vectors for y. You know, if there was just, let's say, one observation I wanted to label, then I would just put in one value for x and y. Also, I want to make sure that my label that I'm putting in there doesn't overlap with the plotting point itself. So if you notice here, I have, for my y coordinate, I have plus 0.1. Obviously, depending upon the context of whatever you're plotting, you might need to change that to something other than 0.1. And then, well, how do I want to label the stuff that's going to be drawn as text in the plot? You could put a vector of characters there. You know, let's say, you know, use the C function, quote, this is observation 1, end quote, comma, quote, this is observation 2, end quote, and so on. Or, in this case, obviously what's more simple is I do 1, n row, parentheses, GPA. Well, let's take a look at what just that little portion actually does. I'm going to highlight that code and run it, and you can see it gives me the numbers 1 to 20. So n row stands for number of rows in the GPA data frame. Remember that colon means the word 2, T-O. So, if I run this code, and take a look at the plot, you can see everything's nicely labeled. An alternative way to label points, and this is very helpful when you only have a few points to actually label, let me just draw a new plot, is to use the identify function, where you say identify wherever your x coordinate is, wherever your y coordinate is, and then the labels that you want to use to identify. And then look what happens when I run that code. So I run it. Oops. Sorry. So when I run that code, look what happens. Oh, look at how my cursor, my mouse pointer here, again, changes to a plus sign because it's expecting me to add information to the plot or point to some stuff, some place where I want to add information to the plot. And so what I can actually do is go over to an observation, let's say this one right here, and if I click on it, look what happens. It's automatically labeled. Click on this one, it's labeled, and so on. And so that's an alternative way that you can use in a more interactive sense to label things on a plot. And if I right-click, look what happens. I have a little shortcut menu that pops up and says, and I have stop, meaning, okay, I'm done. I use identify a lot in some of my functions that I use in my classes whenever these functions are meant to draw diagnostic plots to evaluate how well a model fits the data. In that case, you might be, let's say, plotting residuals, and you might want to label residuals that are outliers. And so this is a nice tool to use for that purpose. Other questions? Okay. So there's a number of different additional functions that are useful. I have examples in my program for how to use them. Please look at them. I just want to briefly mention them here. So earlier today, we've already talked about points. Again, it's just a way that you can add additional points to a plot. AB line, we've already seen that before. That allows you to use basically draw a line of y is equal to a plus b times x on the plot. But it's not only that. It actually can be very useful to draw a horizontal line or a vertical line without the a and the b arguments that we saw last time. So if I use the h argument, that's going to allow me to draw a horizontal line at wherever I specify what h is. So if I say h equal, actually you'll see an example of this coming up, h equal 2.75, it's going to draw a horizontal line on the plot at 2.75. The axis function, I think we talked about the axis before for tick marks, is that correct? Yeah. This is an example of these lecture notes being the first time that I've done them and that I've decided to repeat myself here. Just to review, what the axis function allows you to do is have greater control of what exactly an axis shows. So it allows you to specify, I want, let's say, 0 to 4.5 by 0.5 rather than the default of maybe 0 to 4 by 1. So I give another example of how to use it. There's one thing that I want to mention here that is new to you, and it comes again back to this par function that allows you to control various options on your plot. Okay, let me find it here. There we go. Okay. PTY for par stands for plot type. And simply what that means is, what is the plot, how is the plot going to fill up the space in your graphics window? So if you notice, if I grab a corner or edge of the graphics window here, look what happens to my plot. It expands. And by default, the argument value of m, so quote m, end quote, stands for maximize how the plotting area is taken advantage of. Sometimes, though, you don't want that to occur, and rather you would like to have a square plot, especially in situations where you have a scatter plot where the x and the y-axes are on exactly the same scale. For example, with high school and college GPA, they're approximately on the same scale, approximately 0 to 4. Of course, high schools here in the U.S., you can have greater than a 4.5 or greater than a 4 GPA if you take advanced placement courses. But still, in this particular setting, we may want to control the plot so that it is actually a square plot. So if I say PTY equal S, I get a square plot. And so, as you can see here, when I draw this, now no matter the size of this plot, it's always squared. And the x and the y-axes are exactly the same lengths, which can be very helpful for interpretation purposes. there's a function called mText. M stands for margin, then text. Let's say if you want to put text off the main plotting area and put it into a margin. And so, for example, here's a plot that I have for high school and college GPA again, where let's say that the college admissions office wants to look at a plot like this and make decisions about who to admit. And let's say if a person's estimated college GPA is greater than 2.75, we will admit them. So it might make sense to draw a horizontal line at 2.75 on the plot. And then for illustrative purposes, you could label it. And so that's what I did here. So again, this particular line comes about saying AB line, H equal 2.75. And then LTY would be quote dotted end quote. COL for color would be blue. And to do the 2.75 there, how do I do that? There's the mText function, where the argument text says, well, what do I want to actually be plotted there? Side equal 2 just corresponds to, well, there's 4 sides to each plot, and R associates side 2 with the left-hand side y-axis. Where do I want to draw it at? Well, a y value of 2.75 since I'm on the side equal 2. And then LAS equal 1 equals, give me one moment. My notes here to myself, labels, axis. I think this, no, let's just look it up. Okay, it's an adjustment factor. In other words, and there's different values for it. In other words, it controls, is this 2.75 going to be right in line right there, or is it going to be shifted above 2.75, or is it going to be labeled below 2.75? That's all that means. So that takes us to page 8 then. Now there are times where you would like to be able to use some mathematical notation on a plot. So there's 2 main functions that allow you to do that: expression and substitute. So, for example, let's see, do I want to do that one or not? I guess we could do this one. Unfortunately, for some reason, the example that's in my program is a little bit different. It still gets to the point of what needs to be done. And let's say, so you can see here in the legend itself, this is where I've chosen to do some mathematical notation. So if we look at the first example there, I simply want to put y hat equal to beta hat 0 plus beta hat 1 times x. Why would you actually want to do this for a plot like this? Well, you typically wouldn't. I just want to show you in the context of our previous example, well, this is how you can get some mathematical notation onto a plot. And so if we take a look at the actual code, then. So here I'm using the text function again, as we've seen just a few minutes ago, where at x equal 1.5 and y equal 1.5, I want to write out some text. And then this is where I can use the label argument to say, well, what is the text? Okay. Then what I want to do is use expression, the expression function, to get this mathematical notation there. Now, if you notice here, there's just some regular words to begin with. Example number 1, colon. And then I have separately some symbols. And so basically what I need to do is take this regular text and these symbols and paste them together. So there's a function R called paste that's very useful for this purpose. let's look at a very simple example of using paste. So let's say if I use paste parentheses, temp1, oops, we'll just do this. This is even more simple. Paste together A and B. Look what happens. A and B now form one string, you could say, character string. By default, there will always be a space in there. If you instead do SEP equal quote, quote, then they are joined completely together. Let's say if you have an object called X and it has a value of 1. Suppose for some reason you want to paste the value of X is, comma, if you put X there, look what happens. It's all nicely pasted together. So paste can be a very useful function. Now in our context of what we want to do, we want to paste again example number 1 together with these symbols, this mathematical notation. And so to begin here, inside of the expression function, I say paste, quote, example number 1, colon, quote, and I have a comma there. Then here's my mathematical notation. You basically write it very, very similar to how you would write LaTeX code for an equation. It's not exactly the same, but it's very close. In this case, hat, parentheses, y, and parentheses. Okay, that's going to give me a y with a hat on top of it. Then the place where this is different from regular LaTeX code is I have to use a double equal sign to mean equal. Now remember how R uses single equal signs, that's why. Then I need a beta with a hat on top of it. So I'll just do hat, parentheses, beta, and parentheses. And then to do a subscript, just like in LaTeX, I use square brackets, and then would write one in the subscript. To do the multiplication, I can use an asterisk. And this is all within the expression function. I added an additional argument in text for POS, meaning position equal 4. If you look at the help for the text function, you'll see, well, it corresponds to, well, how do you want to position this text at x equal 1.5, y equal 1.5? And position equal 4 means it's going to be right up, left justified at that value. So there's some values for position that allow you to basically have it centered at the value for x and y that you've designated. Now in the next one, this example number 2, notice how I have actual numerical values in there. And sure, I could have just simply typed the actual numerical values, but I didn't want to do that. That's too easy. Let's actually extract the numerical values from our mod.fit object, which actually which we use to estimate the regression model. So this is how you do that. So rather than expression, you use the function substitute instead. And so again, I'm going to paste, now example number 2, then with my mathematical notation. But you're going to see, you don't have that hat, parentheses, beta, and parentheses anymore. Why? Well, because I actually want to put in a numerical value. And so as an additional argument in substitute itself, you can specify a list. You can actually create your own list that says, I want something that I can use called beta hat 0. I could call it something else if I wanted to. And it's going to get the rounded, I know that's kind of cut off there, the rounded to 2 decimal places for my mod.fit $coefficients 1, my beta hat 0. Also, I want to create something called beta hat 1 that I'm going to use inside of substitute. That's going to have the beta hat 1 value from mod.fit. So that then now my syntax is hat parentheses y, m parentheses, just like before, equal like before. But now, wherever r sees the beta hat 0, it's going to actually replace it with the actual numerical value of 1.09. It's substituted. So that's how you can do that. Now, a great way to see all the options that are available to you to get mathematical notation, to get symbols on one of these plots, is to run at a command prompt demo plot math. Let me just show you that real fast. I'm going to hit enter, and then I need to go over to a plot. Oops, close that out. It's not closing out. There we go. Okay. So it tells me to hit enter, and then I can, through using my mouse key, I can cycle through the various different illustrations of the actual syntax that would need to be used in expression or substitute. Okay. For many R functions, there are demos associated with it. Basically, these are, depending upon whatever the author of the function wants to do, these demos often just simply go through all the examples that you see at the end of the help page for a particular function. Okay. Any questions? Okay, let's talk about the par function again. Now, I think I mentioned this in a class before. Let me actually get a plot up here. So here's my scatter plot again. And I specified my code, as you can see here, I want my x-axis limits to start at 1.5 and end at 4.5. Do they actually end and begin there? No. They actually go a little bit farther out. The default is 4%. Now, there are some times where you want really fine control, and you want it actually to start at 1.5, actually start at 4.5. How can you do that? Well, again, this is where the par function comes in, which controls various graphical options available to you. There is an argument in par for x8xs, which stands for x-axis. And the default, note that the default will always be listed first in a line of possible options. The default is R for regular, which means extend the data range by 4% at each side. To prevent that from happening, use the value I. So, and this is just a screen capture from the help. So, let's say I do par x8xs equal I, do my plot, and then I'm going to change it back to the default. And if I look at my plot now, you can see that indeed it did start at 1.5 and right at 4.5. Now you might be thinking, geez, some of these options, who cares about all these little details? Trust me, when you start doing R plots for various purposes, especially outside this class, oftentimes you want that kind of fine control. And unless you know where to find this kind of information, it can be difficult to figure it out. And so that's where, when we go over these examples with the par function, for example, it can be very helpful that, okay, if I look, it can be very helpful so that, let's say if you have some other problem that you're trying to figure out how to have very fine control over the graph that you're creating, you can always go to the par function and say, okay, let's see if it's there, what I want to do. Yeah, it might be. Well, oftentimes it will be. We've talked about escape characters before, where if you want, let's say, and this was with respect to, I think it was at least it was in the notes. I think we went over in class, but at least it's in the notes for the introduction to R, a section where we wrote the function SD2 for calculating standard deviation. And in a maybe we didn't do that. Well, it doesn't hurt to do it again. I apologize. Does the /n look familiar to you? Okay, no one's replying, so I'm going to say yes, and I'm going to move on. I'm going to ask you a question about it on the test. I was trying to make a joke there. So I wouldn't be surprised if the silence was because, no, you have no idea what I'm talking about with that /n. So if you don't know what I'm talking about with that /n, I at least want a head nod. This, I don't know, or no, I've already seen this before. Well, thank you for one person nodding your head. I'll go over /n because I want to. Okay. There are what I call escape characters in often used in programming languages. And basically that / allows us to do an escape, meaning it allows us to have this n, in this case, since the n is right up against the / sign, to mean something other than the letter n. And you'll find this in a variety of different programming settings, including Linux. And what a /n means in Linux and also in R is it forces then, of course I cannot find the exact example here. It doesn't really matter, but I'll just find another place to insert it. It basically just simply means to go down to the next line. So if I put a /n right here, what's going to happen is you're not going to see the /n, but you will see that indeed high school GPA went down to the next line. And lastly, on page 10 of the notes, I give some information about how to change fonts on a plot. Do note that this isn't quite right here, but I have this morning I uploaded the correct way to do it in the program. Okay, let's talk about how to vary symbols within a plot. And now this is going to take us back to the serial data. Unfortunately, at the very beginning of the notes where I indicate, well, what were the program names of the stuff that we're going to use, I failed to put the program name here, but simply it's just serial underscore graphics. This file right here. And if you remember with the serial data, we have these serials. We have sugar, fat, sodium associated with every serial. And we also have the serials based upon shelf. And we might want to do a scatter plot of, let's say, sugar versus fat, where we have the plotting characters corresponding to the shelf number. And this will help us see trends in the plot. Well, how can we do this now in R? I'm going to read in the data, adjust the data like what we've done before. Do note that basically, we did this before with SAS. Well, this is simply how you do it with respect to R. It's not difficult, so I want you to make sure you read that on your own. So now to do the scatter plot, I need to specify a color and a symbol to use for every single observation in that plot. So that when R does a scatter for the 40 observations, it will look in your PCH argument for what plotting character should I use for this particular symbol. Before, we used just simply one value for PCH. Now I need to put 40 values for the 40 different observations. So to do that, I'm going to create an object called shelf.color. And what I'm going to do is repeat red, blue, dark green, and purple 10 times each. Why? Well, take a look at what we get here. Those are all my colors. And because of how the data is organized, where the first 10 observations are shelf 1, the second 10 observations are shelf 2, and so on, this is quite simple to do. We'll look at an example shortly about that illustrates, well, how would you approach this if, let's say, all the observations were mixed up, meaning maybe you had observation with shelf 2 first, and then an observation with shelf 4 next. Then for my plotting symbols, I do basically exactly the same thing. Where I chose these particular symbols, notice they're represented by symbol numbers. Remember, we had a little table in the intro to our notes that shows what each of those numbers correspond to. I chose these particular symbols to correspond to the ones that I have in my SAS notes. And we did this as well. Okay. Now to do my plot, same as before, or I guess we haven't exactly done this before, but on my x-axis, I put fat. So I grab the fat out of cereal. For my y-axis, I grab the sugar out of cereal. And then for panel.first, I want some grid lines. Plotting character, here are my 40 symbols. Color, here are my 40 colors. And I'm going to put a nice legend on my plot as well. And there's my plot. Notice with my legend here, I allowed a box to be drawn. Also, I put a title on it as well. We hadn't done that before. And you do it similar to as you expect. If I say title equals shelf, that's my title. BTY equal Y for yes, draw a box around it. And that's actually the default. Notice for my legend here, I do 1:4. Notice I'm not even specifying particular, anything with quotes, because I only have numbers here for my shelf numbers. So 1, 2, 3, 4. Notice how I specify the colors, the 4 different plotting characters as well. BGY, what do you think that means? Yeah, the background. I just purposely put a white background there because I thought it was kind of annoying seeing the legend. Seeing the grid lines intersect with my legend. Well, let's talk about how we can do one of these legends without the assumption that that everything's nicely ordered, that the first 10 observations are shelf 1. And to do that, I'm going to transform my my data a little bit. So the first thing I need to do is my shelf variable. That's just some numbers. So I just have some numbers there. Let's take a look at the class of that integer. Okay, that makes sense. These are just integers. But I'm going to use a function that you'll see shortly that basically requires R to recognize this instead as a factor. We talked about factors in the introduction to our notes, where instead of R recognizing this as having some kind of numerical quantity to it, I need it to basically be represented as qualitative in nature, categorical in nature. So to do that, I'm going to use a function called as.factor. You're going to see a lot of functions like this available to you where you can change the class by using an as function. So as.factor, and I'm going to put that into a new variable directly in my data set. Notice how I'm doing this. Here's my serial data set, $, shelf.factor. So this is a quick way that you can add a variable to your data set. I don't think we've seen that before. And then what we have seen before is the use of the levels function. And so if I do that, we can see that indeed this recognizes that it has 4 levels to it. And in fact, if I just show you the whole thing there, It looks like before, but now it recognizes, yes, this is qualitative in nature. It's categorical in nature. And the reason why I'm going to do that is because I'm going to use a function that's available to me in the plier function, plier package, that is going to make my life more simple. And this function actually requires you to have a qualitative categorical variable. So the plier function is the plier package is a very commonly used package in R. It's written by a guy named Hadley Wickham. He's probably one of the most well-known people in R right now. And it allows you to do various things with your data set in a more easier manner than if you were to use, let's say, just the stuff that's available to you in the base package. So you have to actually download it, install it, and then say, hey, I want to use a function from that. Do the library function. Library, P-L-Y-R, in parentheses. Now all the functions are available to me. I know we're a little bit over time here, but I want to finish this off. Okay. Now, what I need to do is this. I'm going to use this. The function that I need from plier is called revalue. And so I'm going to revalue everything that's in shelf.factor, where I'm going to replace a 1, meaning shelf 1, with the color red. I'm going to replace the color. I'm going to replace the value of 2 with the color blue. And so let's actually just run that real fast. Just that segment of code there. Oops. Didn't run it right. And you can see what has happened. Why do I want to do this? Because this will automatically give me my colors that I can use with my plot. That's why. Interestingly, though, the plot function then does not like having a factor. This is a factor. Notice you see the levels there. Does not like having a factor for the plot for the COL argument, and instead it wants it to be recognized as a different class of an object called character. So then I say as.character. I enclose everything then in parentheses with that revalue. I put that in an object called shelf.color2, and there you go. This is exactly what we had before when we used the REP or repeat function. Now those are the plotting characters. In a similar manner, for my symbols, I need everything to be an integer. So I say as.integer, and look how I'm replacing a quote and end quote with just the number 1. Okay, and then when I do my plot again, using shelf.symbol2, shelf.color2, everything will end up being correct. Obviously, that code is a little bit more complicated than what one would desire, but this is the best way that I have found to do one of these kinds of plots. Now, one advantage of using something like the ggplot2 package is that you wouldn't have to do this. It will automatically create the legend for you. The problem is it might not create the legend exactly the way that you want it. Here, if I actually execute the next set of code that's in my program, you'll see my legend. In the end, it's not too difficult once you've seen this once before. Okay, we are out of time. Are there any questions? Okay, then that's it for today.